everyone. So today we're going to have the third lecture in the theorems given by Nikolaos.
Okay.
Lecture will be divided into two parts. So the first part will be 1 hour, it will take 30 minutes break, and another hour.
Okay, well, thanks for keep coming. So what have we done so far? So far we discussed quite a bit around central limit theorems and the Lindeberg principle and the Stein method. And last week I also stopped by introducing the notion of white noise. And yesterday we discussed the stochastic heat equation, and I gave you a glimpse of how this multilinear structure, like the multilinear polynomials that we discussed last week, kind of arise in the study of the model. And maybe I gave you a very high level idea of how Lindeberg principle could be used in order to produce a scaling limit of the stochastic heat equation. So today, what I would like to do is I would like to elaborate a bit on the relation between Lindeberg principle and scaling limit of disordered models. And we will do this step by step. We will not do it in the critical dimension, but we will see also more precisely how the critical dimension arises when you want to take scaling limits. And then we'll work a few examples. But before that, eventually we will be expressing things in terms of chaos expansions. So I would like to introduce the Wiener chaos expansion and start with a little discussion about the Wiener chaos expansion. And then I would like, before that, let's review the white noise. Okay, so I would like, because the chaos expansion will be iterated integrals with respect to the white noise, and I also want to, show some scaling the white noise has, because this is also going to be useful. So I review what is a white noise. So it is a random measure in quotation marks, such that, let's say, if you are for every A, let's say on R D, you ask the W of A, which formally we think of it as the integral of W dx over A, over the set A, to be a standard normal random variable with mean 0 and variance the Lebesgue volume of the set. And this holds for every, so this is equal in distribution. Okay, for every set A in RD. The second that you would like is you would like independence. So if A and B are disjoint, then W of A as a random variable is independent of W of B. Right? So if you have a space here and you have a set A, a set B, so what randomness you have here is independent of what randomness you have here. So the notion of independent identically distributed random variables. Okay, and then we would like to have a notion of a measure. So if you have A1, let's say A and disjoint, mutually disjoint, then the white noise of the union should be equal to the sum of the white noises of the volume, the mass that the white noise assigns on each set AI. Okay, so now, of course, there is a question. Okay, you define this object. Does this object exist? Okay. This is not, there are subtleties here, mesotheoretic subtleties, but for this, maybe I will defer. I will not discuss this. For the first part, including this, actually a good reference is a book by Nualard, Mallam in Calculus. Okay. So Mallam in Calculus, of course, is something that notationally can be a bit not very pleasing at first. And yeah, when I was a graduate student, I took the book, but it wasn't so pleasing, so I put it on the side. And then eventually I learned all these things basically from scratch. But now going back to the book, I say, oh, it's a nice book, actually. Indeed, it's nice. So for some parts I'm going to discuss here, there is this book, Mallam in Calculus. There's another book by Janssen, I think Janssen, Gaussian Hilbert spaces, but I think this is a bit, the level of abstraction is too high, so maybe you lose contact with the substance of things. Okay, so okay, we have these definitions. One thing I would like to deduce now is a scaling. So this is something that I used to motivate the wide dimension 2 in the stochastic heat equation. It's critical yesterday, but let's go step by step. So scaling. Well, let's suppose that you have a set A, and then you want to see what is the Wiener measure on the set scaled up, set epsilon by epsilon. So we have the set epsilon A. Okay, so you have a set A, and then maybe this is epsilon A. Okay, so this would be, by the definition, would be an unknown variable, which would be Gaussian with mean 0 and variance the Lebesgue volume of the set epsilon A. But if we assume we are in D dimensions, so this is, the volume of epsilon A is just epsilon to the D times the volume of A. And then this has the same distribution like epsilon to the D half. Okay, so if you have a random variable, you multiply by epsilon to the D half. This is has the effect that the variance of these Gaussian random variables scaled up by epsilon to the D. Okay, so we have, yes, so if we want, for example, if you want to define the infinitesimal volume W dx, and you would like to do some change of variables, let's say W d epsilon x. So this is like W, okay, so maybe we have two D's here. That's not very good. Okay, so it's spit out in this way. Now, I would like actually to explain how we can use this in the stochastic heat equation. So in the stochastic heat equation, you have ut equals Laplace u plus, what I was writing was xi times u. Actually, in reality, this xi is, so I'm going to write it in this way. So this is Laplace u plus, maybe I'll put a beta here, because it's going to be important, is a derivative, is the density, if you want, is a density of W with respect to Lebesgue. Of course, this doesn't exist because it's a singular measure, but formally, and actually the noise here is space-time noise, so dt dx. So here is the space-time, the noise on the space-time domain. And here by xi, we really understand the density. Okay, so you have a measure, and then, but this is you have a measure, and then this is an equation, which is formally you would like to evaluate it point-wise. So how do you evaluate a measure point-wise? You look at the density. So formally we have the density here. And then what I said yesterday to motivate the criticality was, okay, so y dimension 2 is critical, and we motivate it by as follows. So we look at the solution u epsilon of tx, which is defined as u t divided by epsilon squared, comma x by epsilon. And then we asked what kind of equation does this u epsilon satisfy? So if we differentiate u epsilon in terms of time, we go here, use a chain rule. So we have 1 over epsilon squared, and then we have the derivative of u with respect to time evaluated at t over epsilon squared x over epsilon. But now we can go to the equation above. U satisfies, so this will be equal 1 over epsilon squared Laplacian of u evaluated at t over epsilon squared x over epsilon. Here is 1 over epsilon squared plus 1 over epsilon squared times beta w d of t over epsilon squared, okay, dx over epsilon divided by d of t over epsilon squared times d of x over epsilon, and then I will have u evaluated at t over epsilon squared x over epsilon. Okay, that's the equation that we would be having. Okay, so then we have that derivative of u epsilon in terms of time. So here we can write this easily as the Laplacian of u epsilon evaluated at t comma x, right? So all this now will be evaluated at t comma x. Okay, so it's clear because yes, if you differentiate this function with respect to x, every time you differentiate with respect to x, you spill out an epsilon, 1 over epsilon. Plus, and now is where I would like to use this scaling of the white noise. So what do I have here? I have epsilon, 1 over epsilon. Space is d-dimensional. So I will have epsilon to the d, but when it gets out the noise, it will get epsilon to the d half. Okay. Time is 1-dimensional. So when I get epsilon squared out, I will get the square root of the epsilon squared. So, okay. And then what do I divide here? So I divide, what are the factors I divide in the denominator? So I have to the -1, right? So these are all okay. Yes. So now here I will have 1 over epsilon to the 2 plus d. Okay, maybe d plus 2. Okay, so when I pull out the epsilon from the denominator, and then what I remain with is something now that will have the same distribution. Like, so I put a tilde indicating that it's not actually the same realization of the white noise, but it's something that has the same distribution like the white noise. And then I will have dt dx divided by dt dx and u epsilon of dx, because this object here is u superscript epsilon. Yeah. Now we look at the factors. here, and then we get epsilon to the negative, I guess, d half. Okay, 1 over epsilon. Did I mix up something somewhere? Oh, okay. Of course, very important. I forgot this factor here. Okay, so I forgot this factor. So here we need to have 1 over epsilon squared times beta. Okay, so overall, what do we have? So, right, so here we'll have epsilon to the d half plus 1 minus 2. Okay, and then here I'm going to have w tilde dt dx divided by dt dx u epsilon. Okay, and now this thing here is epsilon to the d half minus 1. So this is the power that yesterday I just wrote in the slides. Yesterday I said, okay, if you look at u, the rescaled u epsilon, then it will satisfy this equation. Okay, the same Stochastic heat equation, only that the strength of the noise is amplified or reduced by this factor. Okay, and from there you can see that d equal to, as we discussed yesterday, is the critical dimension, precisely because it makes this factor disappear formally in the scaling. So you cannot see whether as epsilon goes to 0 or as epsilon goes to infinity, this term here will be very small, will be scaled down and become a perturbation of the heat equation, or it will totally dominate. Okay. Okay. So yeah, I think this is yeah, an important scaling to have in mind about white noise. And now we would like actually to define the integral with respect to the white noise. Any questions about this derivation? Okay. So let's define white noise integrals. Okay. Of course, the basis to define a white noise integral, so we would like to define something like, if you have a function on Rd, what function we need, we'll have to specify. What function is allowed, we'll have to specify. We have integral f of x, we would like to define this object here. Well, what is a standard way to define integral with respect to some measure? Well, you have this 3 steps procedure. Okay, you do it for indicator functions. You do it for simple functions. Simple functions is some linear combination of indicator functions, and then you pass to some limit. Okay. Well, we have already defined this integral. Okay. This is just the definition of what we gave. So this is W of A, and we know what this object is. So it's a normal random variable, a Gaussian random variable with mean 0, and variance the Lebesgue volume of the set A. What about simple functions? So Well, here we can assume that the A's are mutually disjoint. Okay, and we can use property 3. Okay, so this will be just, so by property 3 will be just summation alpha I, okay, if they're disjoint. Okay, then you would like to pass to the limit, but pass to the limit means what? We have to actually define what limit means. So we have to define some notion of a metric. Okay, and then, well, we use the Gaussianity in order to define the isoisometry, which is just basically as follows. So the isoisometry will say that, okay, suppose that you have defined, or for the class of functions f for which this integral has been defined, so far we have defined this integral for the class of functions which are indicator functions and simple functions. So if you look at the expected value of the square of this should be the integral, the Lebesgue integral of f squared dx. So why should we expect for this to hold? Well, this is just the Gaussianity, right? So if, so for example, if f is a linear combination of a finite number of a simple indicator functions, and let's try to compute this. So again, we can assume that AI's are disjoint. This would be the expected value, the second moment of summation alpha I W of AI squared. Okay, and if W's are disjoint, now we will make crucial, that's where the crucial use of the second bullet takes place. The WAI's will be independent. So here you have a sum of independent random variables of mean 0, and the variance of the sum is equal to the sum of the variances. Okay, but the variance of each WA is a Lebesgue volume, WA. Okay. Which now you can write this as summation alpha I, the integral of 1 AI alpha I squared dx. Okay, and of course, I can square the indicator function without changing anything. And then if you do the algebra, again, you have to use very crucially that the A's are mutually disjoint, so that when you take the integral of the indicator function on AI against the indicator function of AJ, this integral has to be 0, because one of them has to be 0 for every x. Okay, so then this turns out to be equal to the integral alpha I indicator AIX squared dx. Okay, so the isometry holds for the case of simple functions, and that's all that we need. Okay, because now you can answer what is a class of functions f for which we can define this linear integral. So the class of functions f is in L2 of RD. Okay. So if you have any function in L2 of RD, you can approximate it in the L2 sense by simple functions. Okay. So now if you have a sequence of simple functions which approximate f in L2, okay, you can build Cauchy sequences. Okay. So you could build a Cauchy sequence So we have a sequence Fn simple. And let's say this approximate in L2 of Rd the function f. Well, we know how to define Fn of W dx. Okay. Then we want to make sure that this defines a limit, has a proper limit. So we form the Cauchy sequence. Okay. And this will be a Cauchy sequence in L2 of P. L2 of the probability space. Okay. But of course, then this we can write as expected value the integral of Fn minus Fm W dx squared. And now by the Ito isometry, this will be just the integral, the L2 integral on Rd okay. But because the sequence of simple functions Fn is chosen so that it converges, it approximates f. So this will go to 0. And then we can define then the integral of f, a general f in L2 for d as the limit of the approximating Wiener integrals on the simple functions. Okay. That's also pretty standard. That's also how the integral is defined. Now, the good thing is that integral, when we do Ito, just one-dimensional. But white noise is something more general. So here we have it on RD, right? So there's no time direction. But still, the approach of defining the integrals against the white noise is exactly the same as if you define the stochastic integral on the real line. Okay. Any questions? So again, I'm referring more to the young audience, even though I also believe that the young audience think this is too simple. The young audience in Taipei probably thinks it's still too simple. Okay. So we defined the iterated integrals, and now we defined the Wiener integrals. And the next thing we would like to define is the iterated Wiener integrals. So how does it go? You have a function f of, let's say, q coordinates, and this, we ask this to be a function on Rd to the q. Okay? So it's a function of k arguments, each one in Rd. And then we define the iterated Wiener integral, so such that, and this is very, very crucial, such that it vanishes on diagonals. This means that f x1 xq is 0 if, let's say, xi equals xj for any possible I and j. If two coordinates are equal, then we require this function to vanish. And that's very important in order to define this object on R d to the q, fx1, fxq, w dx1, w dx2, w dx3. So this is called the iterated linear integral of order q, and often is denoted, at least in Nikolaos' book, by iq of f. Why it's so important? I mean, we will not construct this integral, but actually the construction follows exactly the same steps like what we did in the one-dimensional case, in the single, not one-dimensional, in the single linear integral. Okay, so you define this object for simple functions, for indicator functions, then for simple functions, then you take a suitable L2 approximation. I'm not going to proceed with the same. Again, you have the L2 Ito isometry, which maybe I'm going to write it. So the Ito isometry says that the expected value, the L2 norm of phi cube f, is equal to the integral, the L2 norm of the iterated, of the multiple integral of f. Okay. Again, how you obtain this Ito isometry? It follows from consideration with the simple functions. Right? The simple functions will have this Ito isometry, again, because of the properties of the white noise, the Gaussianity, the independence, and the linearity. And then you extend this again to any suitable L2 limits by taking approximating sequence. Why vanish diagonals? Well, let's look at a simple example. Okay, so let's have fx1, x2, w dx1, w dx2. And then let's look when x1 and x2. So let's look at the integral x1 equals x2. Then formally we would have something like this. But we cannot write something like this. This is the analog, like writing something like the delta function square. You cannot write the square of a delta function. The square of a delta function is not defined. Okay. So that's why the iterated integrals appear being defined on off diagonals. Right. You can also see this example what will happen if f was a kind of a sort of an indicator function concentrating on a diagonal. Now, but this is actually an extremely important point, yes? The diagonal, yeah, because it's like having a delta function, because like you have a function f of x, so the delta function only happens at 0. Yeah. Still the singularity of the noise does not compensate, just a single point. Yeah. Yeah. So you have to define it. Yeah. You have to exclude diagonals, and then you have to do some procedure. Yes. But formally to define this is so you assume it vanishes on the diagonals. So actually, this is this point also is very crucial. If you want the normalization theory, has to do with this thing. In also in the theory of regularity structures, but already way before in quantum field theory. Yes, you have a question? Yeah, we can take simple functions. Approximations, yes. So again, you can play a similar game. So suppose that you have similar, another, well, if you want, you can have another sequence that converges. Okay, but again, you can play a similar game so that because the limit is in L2. So if you have different sequences converging to the function f, necessarily they must converge to the same limit because you have this L2 contraction. So we define the linear integral in this L2 sense. Is in an L2. Yeah, because yes. So it's stronger, yes. We asked for something stronger, yes. Okay, thank you. Right. So I was saying about this kind of diagonal, because actually in mathematical physics, you can have situations where you have function here which hits diagonal, and then this thing kind of becomes infinity. And in order to define it, so you have to subtract something which is infinity. In order then, I think this is also related to your question. So you subtract this infinity, and then what remains has some kind of stable distribution. Okay. So if you want maybe take-home message, if you would like to read the normalization theory, or if you know all these developments in stochastic PDEs, which involve, in stochastic PDEs often they write how do they make sense of the KPZ equation, let's say. Okay, this doesn't make sense precisely because this white noise will be distribution. Then you square it, which is a thing that we said you cannot do. You square, and they always write this is in a very mysterious way. Okay. Yeah, don't quite. Of course. If it feels like being in a club, right? So you know the code, the code of conduct in the club, but this is just to keep outsiders out. But this infinity again has to do when you want to start solving this equation, you start doing some Picard iteration, and in this kind of situation, you will end up with some stochastic integrals, some linear integrals of this form, where you cannot exclude the diagonal. And the diagonal will be infinity. So you need to subtract this infinity. And now it's also very important, actually, because there are many infinities. So what infinity do you need to subtract? Okay. And actually, formally, they write something like this, but actually, the procedure is that you modify the noise like I showed yesterday, you integrate the white noise against a smooth function. So psi now is a smooth function. So this is perfectly sensible. Then you solve this equation for every epsilon, which you can have a solution theory. And then you need to identify a constant C epsilon, which has a very precise form. I think if I remember correctly, in the case of KPZ in dimension 1 is probably log epsilon, if I remember correctly. This is, I may be mistaken, but even this log epsilon is very different than the log that I was having in the critical case. So by looking at the chaos expansion of the solution of this equation, which comes through Picard iteration. Maybe I'm going to write this in a minute for the heat equation to remind you how it works. Then the Picard iteration will involve integrals of this sort where the diagonal is not excluded a priori. And then you have to identify how to basically here you will have to to subtract something infinity, and this infinity is basically the L2 norm of this object. Okay, now I'm becoming a bit sloppy. So this is going to be basically essentially the L2 norm of the diagonal. Okay. Right. Okay. So just keep in mind that yes. So the Wiener integrals formally are defined only in cases where you don't want the noise to coincide. You don't want to have a situation that you may be squaring the white noise. Okay. If this happens, you need to subtract it. We need to subtract these terms. This is going to be infinity, and this infinity, which then you compute precisely depending on what kind of stochastic integral you have. This infinity is what determines eventually what are these infinities that you subtract in the constants. Okay, I didn't give any details. I just told you a bedtime story, but yes, right. Okay. So we defined the notion of the iterated Wiener integral. And now there is this very, very important theorem, which says that take any function f, any random variable f on L2 of the probability space. Okay, so you have a probability space, omega fp, and then you look at the L2 variable on this probability space. Any L2 variable can be decomposed as sums q greater or equal to 0 of iterated Wiener Ito integrals for functions fq. So in other words, let me also unfold this. So this summation q greater or equal to 0. Q equals 0 is a term that is a constant term, the non-random term. Okay. By the way, one more thing that you would like not to have squares is because you would like this to be orthogonal, these families to be orthogonal. So you would like this to be mean 0. If you had w squared, when you take the expected value, it wouldn't be 0. Okay. If I take the expected value of this is mean 0 because dx1, dx2 will be different. So expected value of w dx1 times w dx2 would be equal to the product of the expected values. But by the fact that the w is mean 0 and random variable, the expected value of w dx is 0. Okay, so that's another reason why we don't want to have diagonals, because we don't want to have w dx1 squared, because this wouldn't be mean 0 anymore. Okay. Okay, and then let me conclude here. So we can have so this is the theorem. Again, you can find this in the book of Nuallard. Any L2 function has a Wiener chaos expansion. Okay. So you can see Wiener chaos as a harmonic analysis on the probability space. And of course, it's not it's not by coincidence that Wiener discovered this, because Wiener was doing harmonic analysis. Okay, so this is a harmonic analysis expansion. One difficulty, of course, here, as always in harmonic analysis, to determine these coefficients, DFQ. Often, these are related to Hermite polynomials. But let me not, this would take time, so let me not discuss this. Yes, so yeah, Hermite polynomials, the Hermite polynomials actually, okay, maybe I'll make this comment. The Hermite polynomials actually does this subtraction that I was saying. You subtract the squares, right? You do weak orderings. So the Hermite polynomials gives you a Gram-Schmidt way to produce this decomposition, the orthogonal family decomposition. Okay. And precisely make sure that here you remove whatever is on the diagonal, but it has to be done in a particular way. Okay, but of course we would like some concrete ways to handle this. I would like just to give one example, which I think is also quite important. So I'm going to discuss the weak exponential. Okay. So let's assume that we have a one-dimensional white noise. Essentially, one-dimensional white noise is a derivative of Brownian motion. Okay, so we have the usual notion of stochastic calculus, and then let's say I have a function f, L2 of r now, and then I would like to say something about these iterated integrals, ft1 times ft2 times ftk, w dt1, w dtk. And the integrals are t1 less than t2, t1 is bigger than 0, t1 less than t2, less than tk, less than t. Okay. So here we see I have already excluded the diagonal, so I have strict. Okay. So what is this iterated integral? So the claim is that this is the exponential of the integral of f of t, sorry, f of s w ds between 0 and t minus 1/2 the quadratic variation. The quadratic variation of the integral. Okay, so quadratic variation in this case would be 1/2 times the L2 norm of this. So let's try to check this, maybe just by simple Ito formula. So let me assume that people are familiar with the Ito formula. Or maybe let me write, so if you have a semi-martingale xt, how do we think of semi-martingale? dxt equals, let's say, sigma of xt, dbt, b is Brownian motion, okay, plus, let's say, b of xt dt. Okay, and then we would like to differentiate dfxt. So this will be the derivative of xt dxt, and here you will be going to plug in this term plus 1/2, and this 1/2 is very closely related to that 1/2, the second derivative of xt times the quadratic variation of xt. In this case, the quadratic variation of xt will be just sigma square xt dt. Okay, so this is Ito. So we will derive this by Ito calculus. Of course, again, this is much more restrictive. Okay, so what I wrote here about one-dimensional noise actually is true if the noise there was d-dimensional. But we wouldn't be able to give the proof using stochastic calculus. Okay, because stochastic calculus, we have a time direction that we differentiate. But the remark is that the formula that I wrote, you could replace T1 and T2 as RD valued random variables, and W will be a noise on the d-dimensional space, and you can have exactly the same relation. And this is what is called weak exponential, or weak renormalized exponential, and often is denoted by exponential f s w s with two dots, left and right. Okay. So if you see these two dots, it will be the exponential. So in general, if you have a random variable x, you define the weak exponential or weak ordered exponential of x as the exponential of x minus 1/2 its quadratic variation. Okay. Now, in this case, the quadratic variation of the variable x, which is a stochastic integral, is just the L2 norm. Okay, so yes, the remark is that, yes, the fact that the iterated integral is equal to the weak ordered exponential is a fact which is true beyond one-dimensional case. Okay, so let's try just to convince you that I'm not lying, just to check this in the one-dimensional case using Ito calculus. So how will we do it? Well, we will differentiate. Let's differentiate both left and right side and see what we get. So I go upstairs and I write 1 plus summation k greater than or equal to 1. And then I want to break the iterated integral into two parts. First, I do the first k minus 1 variables. Okay, and then I go t1 less than tk minus 1 less than tk, and I put the tk in red because this is not included in this integration. And then I integrate ftk w tk. And now if you differentiate with respect to time, okay, well, the one will be killed, and then essentially this tt will be killed. Okay, so here actually, in fact, yes, I can even, yes, okay. I can even put the summation inside here. Okay, so then if I take the derivative, I will have, this is going to be killed, I will have summation k bigger than 1 of the integral okay, and this will be integral between, okay, and the tk of course will become t, right? If I call the whole series capital F, well, here I just get capital F of t, right? I have the same series. You see, I have summation k greater or equal to 1, but then I sum over k minus 1. So if I change k to k minus 1, it's as if k minus 1 goes from 0 to infinity. So basically here, what I see is a f. So here, if I call this f, so I see that this is equal to f of t, yes, little f of t, w dt. But I could use also Ito's formula and differentiate directly the exponential. So let's try to do df on the exponential directly here. Okay, so the function that I want to apply to formula is the exponential. Okay, the exponential of this object. So what I will get is the derivative of the exponential evaluated at this random variable. At this random variable, so I will get again f, and the f is going to be actually. So I'm going to get f. I'm going to get f times what is inside the integral. So I'm going to get f of t w dt minus 1/2 f squared t dt. Okay, but now I have to go to the next term in the Ito formula, which is the second derivative. I deleted the Ito now here. So what I wrote is this part here, and now I need to write this part. But the second derivative of f of the exponential is again the exponential. So I'll have 1/2 f, and the quadratic variation here will be the quadratic variation of of this process. But this is just, if you have constant, the constant don't contribute. Not the deterministic terms don't contribute to the quadratic variation. So you look at the quadratic variation of this. So it will be the square times the quadratic variation of Brownian motion. So it's going to be f squared t dt. And this term precisely cancels this term when multiplied also by capital F, which is the exponential of the stochastic integral minus the quadratic variation. So eventually we get the same equation. So the right-hand side by Ito formula satisfies the same differential equation like the right-hand side that I have here. Okay, so that's one way to check that the iterated linear integrals of these multiplicative functions is a weak exponential, and that's a very, very important result that you can be using it as like the derivative of the exponential is the exponential. So that's how often it's used. Okay, are there any questions? Okay, so I think that's actually a very good point to stop, not least because I think they have started serving the tea. And now we concluded one section. And now in the next hour, I'm going to show how these iterated integrals and the Lindeberg idea can be combined to produce scaling limits of disordered systems, let's say random field easy model or direct polymer models and so on. Okay, we'll resume in half an hour. Are you?
So it's something that yeah, this is more complicated question. Yeah. Yeah. Very bad.